Hello everyone, thanks for having me. I'm Andre. I am officially unaffiliated because you know the tiny text box when you register that says what you are, you can be tempted to put anything in there. Actually, you can't put anything in there. Someone just goes through a list and removes it if it's too outrageous. So I put unemployed here, and that's too obscene for TOEFL. And it's just a joke because PhD students are not technically employed by the universities in the UK. If you can't change this, please help your students. But I'm at Strathclyde with Bob Atke, who's right here, and I want to talk to you about syntax. And that is actually not true. This is a trick to make you come here because everyone loves to hate syntax. What I really want to convince you of is to think about syntax as a means to an end. At the end is programming language user experience. So whenever you're designing a programming language and you talk about syntax, you might be tempted, or you might notice that in the discourse, you see people doing things like this, where they have an idea of what syntax means or what syntax is, and they're like, oh, I think syntax is too rigid, or sometimes it needs to be rigid, and those languages are good or bad because they do those things. And you could summarize them by putting features, then assign them a place in the spectrum, and then if you really want to go full flame war, you can say, well, everything this side is actually legible and everything this side is actually rubbish. The other way to see this is like the bike shedding argument, right, where you just keep piling on colors until you end up with a complete incoherent mess that nobody can actually tell what is going on or why this argument for this specific part of the language is useful or isn't. So instead, what I want to have in mind in this discussion, and there's a mistake, but that's fine, is let's think about what is a compiler. I see a compiler as this infrastructure where we have an interface, we have something that users put things in, we have an internal state that is the thing that we usually work the most on, which is also the most important, and we have an output, which is what the compiler produces. In general, this is very binary, or this is either yes or no. And if it's no, sometimes there's a bit of information about why, but it's not always necessary. In reality, what I want to convince you of is that there are three pillars of design that I think we should keep in mind when we're talking about programming language design. And the first one that is actually doesn't need to convince anyone is trust. I'm saying this because we're at WITS and we're writing compilers with dependent types, which probably means we like writing programs and we like writing proofs about those programs. And a big part of this is to be able to trust that the internal state of the compiler or that the types do what we think they do. And what I identify in this previous picture is that trust is about this interaction between what we put in and what we get out. So if we put in types, if they're correct, or if our program is correct, then we get a good response. And if we get a good response, we can believe it, right? This is another way of saying we want, in general, it's a good idea to have a sound type system. Like we can believe it, we can trust it, and it's going to do something that we expect. But there is another aspect of trusting a programming language or trusting a system like this that has an input and output. And for this, I'm going to take an example that's been in the news recently. Can you trust the output of a frozen UI? So this is a quote from one of the articles. A post office operator would see the screen freeze, and then they would keep entering enter, and then the computer would do something, but it would not be reflected in the user interface. This is something that thankfully doesn't happen with compilers, but it does happen a little bit with things like text editors or like IDEs, where you're doing something, it's not quite working, so you just do a clean build, and then it's working. And what is the difference? Who knows? Cached files, internal state, mutable state. Those things happen, and they do erode this concept of can we trust the system. Another way of seeing this that's in the literature is the concept of Pollack inconsistency, that can you believe, or can the compiler believe itself when it generates output? So if you give it a file, it parses it, compiles it, and then gives you some output. Does this output actually match what you've given it, or is it even valid syntax? And if it is it even looking like something that it's advertising? So you can have something that looks like a proof of false, or something that doesn't look like a proof of false, and actually is or isn't. So that's the first pillar of design that I want to keep in mind. The second one is diagnostics. And this one is a little bit harder to convince people that it's important, and it's a property of purely the output. So when you have a compiler again, you have some input, some output, and whenever you get a result, if it's yes, you need to trust it, but if it's no, you also need to know what you're supposed to do in order to turn it into a yes. Again, I'm sure we've all written proofs and programs, and we ended up with a decision like this, where you get a type, and you give a goal, and you put your goal in your result, and it says, oh, my goal is A, and I have a function that returns A, and I just put it in, and it's not A, because there's some hidden state, there's some hidden parameters. It could be anything, right? That's an example of the output or the diagnostic being unsuitable for the usage of making actionable feedback. Another one that's very memed upon is C++ templates, where you just get a barrage of data of this is what's supposed to happen, this internal state, but we actually have no clue what we're supposed to look at. Where is the one function call that actually makes this internal state erroneous? So there is a spectrum. What I mean with those two examples, there is a spectrum between too much information that's unactionable and too little information it's also unactionable. You need to find a compiler diagnostic that makes errors actionable. And the third pillar of programming language design, I've called it self-evidence, but I don't think there's a very good word for this, but is a property of the interface itself. Like files you put in, text you enter, or maybe diagrams you draw. A very successful instance of this idea that you probably heard of this is the Zen of Python, which is a very preachy text, but does, I think, succeed in saying that we need to care about this, this part of the experience. And the idea is basically that things that ought to look like they should work, and things that probably shouldn't be there, probably shouldn't be there. This is very tautological, and it's the hardest one to convince people to care about because, of course, we can't measure those things. Those are purely internal fuzzy feelings about text and syntax. There are other things, if you go to industry, that people with big words like to say. So we want to optimize review speed. We want the smallest diff possible. People who do Haskell love small diffs, for example. We had a very fast iteration time. If you're using Go, this is a big one. Developers are big into I don't want interruptions. I want to keep my flow state as long as possible. Those are, again, very hard things to describe and things to optimize for and to share. But if you go into other industry, the one that I found quite funny had a very good way of explaining this that was quite understood by lots of people is this idea of game feel and game development, that when you are prototyping something and you're testing it, it must feel good to everyone doing it, or you must at least not feel terrible, or identify things where it doesn't feel bad, and then either accept that those things are going to be bad, and or maybe think about a way of solving it. So that's the context in which I want to bring up the topic of syntax in programming languages, and specifically dependent types. And that is because I've encountered a problem, and I want to fix it. But not in the way that will reach a discussion that is exactly like a bike-shedding discussion where just people want to throw their preference and then not really think about those three pillars of design, which is experience, feedback, and surface syntax. So the problem that I want to solve, that I've encountered too many times, is also that probably lots of compiler engineers here have this problem where they only fix it whenever it happens to them, and then we need this to happen. This is a problem, this is a type that occurs in dependent types very often. You have a first argument that is the type of the thing that you're dealing with. You have a second one that's indexed over the first, and then it gives you an output. Could be anything. Could be a type, could be a constructor, etc. A very common example of this is sigmas, right? Give it a type, give it an index, and then that gives you a type. Here another one, pi. We're not breaking any grounds, right? This is normal everyday dependent programming life. Those happen all the time. The one that actually killed me when I was dealing with this is the type constructor, the data constructor for containers. It is exactly the same shape. It gives you a container. You don't have to know what's a container. You just need to know that those three things are in our everyday life, and we have no real way of dealing with them. That's not true. We have syntax. We have special syntax for pi. We have special syntax for sigmas. But we don't have special syntax for containers. And I don't think we should. But I also don't think we should deal with the problems I've encountered. So here's a very simple example. This is very basic Agda, where I'm writing a sigma here. And we have a program here that says that's the index over this type. And I mean, it's a legit program with the lambda and the return type. The problem is whenever you start nesting them, you completely lose the symmetry between what's on the left of the sigma, what's on the right of the sigma. And you have all those lambdas that, what are they doing in types? This is terrible. I showed you C++ templates before, but as dependently typed programmers, we are not immune from this problem. Our types are programs, and whenever we get a diagnostic from type A doesn't match type B could be a very big program, and we actually have the same problem as C++ in this context. Here's what I was going through in my life, which made me reconsider my choices, which is an operator on containers. And there are actually 3 terms in there, but they're all indexed, and they all have lambdas in them, and it's unreadable. So what is the solution? As I said, there already are solutions for pi and sigma. Turns out people have thought about this before me, and we have a solution in both Idris and Agda, which are the 2 languages I usually use. And those are arbitrary syntax blocks. They work the same way. Also, this is Idris 1, I would say. Idris 2 does not have arbitrary syntax blocks, and I think it's a good thing, and we'll see why very soon. What they allow you to do is to say, whenever you encounter this piece of syntax, actually means that. Whenever you encounter this piece of syntax, actually means that. Flip, but whatever, you understand it. It means you can write sigmas this way, which is a lot more natural if you are used to mathematical notation. It also means that you don't need to put parentheses on the right side. You don't need to add lambdas. The programs you're writing look a little bit more like you would expect from your everyday life of programming or looking at types or type systems. If you look at the complex example, you have it's a little bit more complicated, but it's only complicated up to the point that the program itself is complicated. So you do actually recover this this symmetry between left and right, and inside here there's another left and right, and it's much easier to see what's going on. But remember the first part? The idea is not to only think about one of those pillars of design, but all 3 of them. And this solution only fixes the front-end part. We are not explaining how this makes the code more trustworthy, or not explaining how this makes compiler diagnostic better. You could argue, I think this is why I'm not going to talk about it right now, but you could argue that this makes code more trustworthy because it's easier to see, or rather it conforms to our social expectation of what a sigma type looks like, and this social conformance makes it a little bit more easy to convince other people that the 2 things that we're looking at are doing what we expect. So there is another problem, and that's diagnostics. If you don't import the right thing, or if you import or use the wrong syntax slightly incorrectly, you get errors that do not tell you what you're supposed to do. So in this case, for Agda, it just tells you the thing is not in scope. It's just not the right, not written the right way. Sorry, it's just not importing the right module. And this one is the same thing. It says I was hoping for a type signature. You did not give me a type signature, but it is in fact a type signature. So what is the solution I came up with? And that is something that is I've called a customizable binder syntax. And if you use the Camel, you're probably screeching right now because there's lots of binder things in Camel. I want to specify that this is specifically inspired from this dependently typed structure of we have one type, another index, and then a return. Now, if you talk to people in the community and you say, I want a customizable binder syntax, the discussion usually goes like this. It's like this meme of this kid that goes to grocery shopping with their mother and that says, Mom, can we have customized binder syntax? And they're like, but we already have customized binder syntax. What are you talking about? And what customizable binder syntax is at home, it's do notation. Please do not do this. This is actual valid syntax. It does work. Do not. And I see Simon is It's this is Idris code. You can do this in Idris. So what I've reached is this solution. Again, it's complicated, but my argument is it's only complicated as much as the program itself is complicated. So we have an operator here that works a bit like a pi type. So it has a binder on the left and it has a program on the right. And here we have a sigma type that works, exactly like a binder, right? So you have a left bit here and a right bit here. And you have another sigma type, you have a left bit here and a right bit here. And then you can start deciphering what's going on. Anyways, because this is a sigma type that works as a pair, right? So we're pattern matching on the left bit and the right bit, which puts X and F in the scope. And then we're using X and F in the right part of this binder, which is the data constructor for containers.
So this is not active, this is some proposed extension.
So this is my implementation of it in Idris.
Oh, so this is Idris code?
This actually working.
Okay.
But it's not in the compiler right now because people are, discussing about it. So the way it works is very simple, thankfully, because there is a very well-known desugaring that you can do to implement lit binders, and that is to write them as Lambda application. There's one more thing that we need to understand in order to implement this feature is that you can see this as applying the application function, flipping it to those two arguments. And this is exactly what I've implemented. So given an identifier, parentheses, a pattern, colon, an expression, and then another expression, you desugar this by applying the function from this identifier to those things. And the thing that's a little bit special is that the type of lambda is informed by the type of the first argument, which I found quite neat. Does respect exactly what you imagine doing. It works the same way for operators. So if you have on the left a pattern, a colon, an expression, an operator, and then another expression, this does desugar as applying the operator in its normal application, or in its application, its left to right application form, and then the lambda as an expression. I'm not saying like I am a genius and this is incredible. I'm just surprised that this does not exist yet, and all the solutions that we come up with are worse in the specific way that if you write this and you write it wrong like that, you get an actual good error message. You don't get, oh, this thing is not in scope, or I don't know what you meant. You get something that tells you what it is that you try to do, what it is that you should be doing, and what is their possible mistakes. So and specifically, it tells you this is the correct syntax. If this is not what you meant, you probably mean to fix the way you have defined the operator. And if this is not what you meant, you probably need to import the correct thing. And by the way, the things are in those files. And there is also explanation about how to use this. And the reason we're doing this, or the reason we're able to do this, is that unlike arbitrary syntax blocks, we're dealing with a fixed grammar in this language. Even though we have this feature of binders, we know what the file looks like every time. We don't have to guess or try to import other files to see what things are supposed to do. So now, of course, I would not do this if it was just for me, right? If it was just for my small use case of containers. So there are actually a lot of other use cases. The first one I think everyone will be excited about in this specific room is that for loops are back. This is a slight variance where the types are not dependent, but this is basically applicative for written in this syntax, which makes code look imperative looking code look actually imperative, which is quite nice. Something that is very going to be also popular or unpopular, depends on who you are, is math syntax is there to stay. So you can write things like exist x of type p such that f, or for all x, blah, blah, blah. Or you can write the infix form for sigmas. Something that is specific to Idris 2 is that we have linearity, and we have an operator for linear functions, but it is not dependent because it is not built in. It is user-defined. Is there a way we can write a user-defined linear dependent arrow? And we can. And this is what I've come up with. So the dash at is the linear arrow, and the equal at is the dependent linear arrow. And then there are arguments about if you can allow overloads, et cetera, et cetera, et cetera. We're not there yet. The point is that we can do this, and that's a neat, useful feature. And if you're curious, this is the type signature for the function that replicates one element in a vector of n things. So it takes a linear natural number. It also takes n copies of x, and that it puts all those n copies inside a vector of length n, which is, yes. Sorry. Finally, something that is very common in non-dependently typed is DSLs. So I was working in this other dependently typed programming language, and I was writing the elementer for Sigma. And it's atrocious to write if you don't have a better syntax for this. So this is what you can do. And once the floodgates are open, you can do anything. I don't recommend you do this, but this is a data structure that I came up with recently, and it was writing lots of lambdas for the second case, and I realized, wait, I can't just use the feature I just read it. It's just easier. So to summarize, this is how we just usually build compilers, or we build any product. We find a problem, we identify the tools, and we test it, and then we're done, and then we start over. Again, when we talk about syntax, I feel like we skip a lot of those steps. Usually the problem is not really identified properly. We just say, I don't like the way it looks, which is not really useful whenever you have a big compiler with dependent types that's supposed to be correct, and that's supposed to be believable within a community of proving theorems. This feature, I mean, it's a desugaring step. It's nothing magical, but I think the best way to present it to this audience is to, given there are a lot of people who deal with compilers, think about the procedure in which they implement new features in their programming language and take more seriously this idea of both diagnostics and trust in the system. We're extending it because we're never done with work, so this is purely syntactic, but it would be nice if we had first-class access to binders. Let's say I have an X and Y. Can I just know actually how many binders I have? Can I move them around? Can I rebind things when I notice something is wrong? Can I use this to give even better feedback? I've done this for Idris. I don't know how I would do this for Agda. I don't know how you would mix this with syntax blocks. Please, if you know, tell me, or if you're interested, tell me. And in general, I'm also interested in finding out the way we're doing, or the way I've implemented this idea of can we trust the compiler, is that when you resugar code, you also have to take into account the fact that you have done one step of desugaring before, which means you need to redo it once you show it to the user. Is there a better way to deal with this rather than having ad hoc code every time? Is there a bigger theory of let's have the internal state be rendered in a way that is consistent with the way it's been given to us? That's the end. Thank you for your attention.
We have a few minutes for questions.
Thank you for saying that diagnosis is Thank you for saying that diagnoses are important. Yeah, I'm going to give a talk on that. But this is something about keep bothering me. In the diagram, the arrow to the output
yes.
are bidirectional.
I said it's a mistake at the beginning. I was referring to this. I said there's a mistake here and skip. Yeah, instead of ball array should be a single arrow, but yeah.
So I might be missing something obvious about maybe the context or the way you're doing this, that this isn't an issue, but ordinarily when we're encoding things like syntax with binders in some kind of meta level, we don't want to use like the meta level function space, right? Mm-hmm. We don't want to use like functions because then we get we can't faithfully represent the things that we're encoding. You can, if you can case analyze on your input, then that's not,
right.
Correct. So do you have a similar concern here, or is that somehow not an issue?
It is an issue. This is why this is why Edwin is working on the new core with case analysis inside lambdas. I'm just not dealing with this. That's my solution. But it is a identified problem, yes. Okay. But thankfully, it's unrelated to this, right? This problem existed before I've implemented that.
All right. Thank you.
Any other questions? Okay. Well, thanks very much, Andre. And we have